Welcome back, my sassy OChem 1 class. Let's get some more videos in on our bromines. This is so exciting. We're going to keep going on our alkene additions. These are so much fun. I'm going to scroll up for a second. Remember some of the things we've already looked at. Oh, all right. We looked at HBr in water. We've looked at HBr and DCM in our previous videos. Here's our HBr and DCM. And what we noticed in all of those is that we're following those rules to carbocations. And our carbocations rules are following that tertiary. Oh, why am I not drawing? Hang on. I'm going to write them and then erase them, so you may need to pause. So our carbocations, we've got tertiary is much better than secondary, way better than primary. Now, our carbocations and our radicals follow the same process. So in our HBr reactions in our previous videos, we were making those best carbocations. That's how we decided that best choice when we were swinging both ways with that alkene. So we always ended up with our bromine on the most substituted. And that's exactly what happens when we do our bromine and light reactions as well. So just for an example, what happens when we treated this with HBr, where did your bromine end up? Right there. If we treat propane with Br2 and light, where did bromine end up? Right here. Well, our next series of reactions, these next two, are a little bit more modern. The first one is older, but look at where our bromine ends up. It ends up on the least hindered carbon. So this is new. In fact, on our next exam, we're not going to use chlorine at all, because if we choose our bromine reagents wisely, we can either place our bromine here in our most hindered or here in our least hindered. So what's different? Okay, what's the one thing that's different in there? Look at that reagent, peroxide. So our other mechanisms were polar. This mechanism, so our other HBr reactions up above, those were all polar. This reaction is radical. So let's draw an intermediate for that and see why that's different. And then the same one down here, both of these are radical. All right, so take a screenshot for a second. I'm going to add to this list of carbocations, but I want to actually draw out that first reaction first. So I'm going to erase. This is so fun. Okay, so this first reaction, there's only one thing that's different, and it's actually a dirt cheap reagent. That's peroxide. So this reaction is actually fairly old. It's been around for a little while. It is a reaction that now we've got somehow our reactivity is different because now our bromine is here instead of here. So something is different about this process. Well, the first thing that happens in this process is your peroxide. Okay, peroxide, all it needs is just a little nudge. It can be a little bit of heat or a little bit of light, but something is going to come in here and break that bond. And guess what? That is oxygen and oxygen. That is going to break homolytic cleavage. It is going to break even Steven right in the middle. And what does that give us? Radicals. So peroxides are actually pretty good radicals. That is the first step in this reaction. We're about to make two here of these oxygen radicals. We just made two of those. This is our initiation step. Now, I'm probably not going to ask this mechanism on a test. There's a couple things that can happen with this initiation. The most common to draw out is that this reacts then with your HBr. And this does that hydrogen abstraction. Remember, our radicals have that little one-headed arrow like a little fish hook. And this is now a source for us of a bromine radical. So it's kind of a, oh, that's huge. This is kind of a fancy way of generating a bromine radical. Now this bromine radical is going to react with our alkene. So let me kind of continue underneath here. Let me continue that mechanism. Now this is where it gets just a little bit funky. We've got a bromine radical, and that bromine radical is going to react with the electrons in that double bond. So again, we have choices. We actually have 2 electrons in that bond. We have choices, so let's draw them out, which one we think is better. So we could form a bond here with our bromine radical, and that's going to leave behind this radical. Now, how did that happen? That was, if we want to draw the mechanism for that, that would be this electron and this electron just formed a bond. And then we have the other option. Remember, we've got this side as well. So we could also form here, form that bond to bromine. We're getting a little cluttered in here. I didn't give myself enough space. And this radical. All right, what's your gut tell you? Which one's got the better radical? This one. Okay. So this is really interesting. This reaction's been around for a while. Just switching to radicals, what's the main difference in this reaction? Well, we ended up adding the bromine first. So we're still following the same rules we saw in the last reaction. We're just using radicals, and this time our bromine is doing the addition first. And then now we've got this substrate in between that is actually quite reactive, and what this will do is then react with another HBr. So that peroxide is truly an initiator. It just needs to give one radical, and then now the reaction is going to propagate itself. This radical can react right here, and now we can generate more radicals. So that is truly a propagation. And then how would we terminate? We could terminate with anything. We could have 2 bromines smack into each other. There's all kinds of ways to terminate this. But I wanted you to see this intermediate, that this radical is the best radical. And that's the radical that's going to give us that bromine substitution. So our product then ends up with bromine on the least substituted, not the most substituted. So isn't that awesome? That's pretty fun. So again, I probably won't ask this mechanism. It's a little bit bigger. You know, we've got lots of different propagations and lots of different terminations, but it does follow the pattern of our radical mechanisms. Remember, radicals are always initiation, propagation, termination. We definitely have that. This is our initiation. And then our termination could be maybe 2 Br radicals find each other. We've got lots of different ways that could happen. All right, so then let's go ahead and screenshot for a second, because I want to show you the second one. Okay, so how do you get bromine in the least hindered? You throw in a little peroxide, and now you've changed your mechanism from polar to radical, and you've changed the order. You've actually added your bromine first, not your hydrogen. So we got the least hindered on there. All right, let's look at this second one then. This is my favorite. So HBr itself is actually quite a sassy reagent. It is a very strong acid. It'll fume like a mother as soon as you open the bottle. We used to use it in our OChem 2 class, and it's the reason all of our glassware is etched. So if you ever use your round bottoms in your OChem 1 lab and you're wondering, God dang it, the last class didn't clean their glassware. No, your glassware is clean. It's just literally been etched by the HBr and that experiment. So HBr was a really powerful acid and used a lot back in the 50s, 60s, 70s. But then an actual source of bromine that could be shelf stable and could be easier to use. You know, there's a lot of reasons to want to use an alkyl halide, and if your only reactions mechanisms to make them are really toxic and a pain in the butt to use. It was only a matter of time before somebody developed a nice, stable, much easier source of bromine, and that's our NBS. So let me draw out what NBS stands for, but it is okay for you to just say NBS on your tests or on your homework. NBS stands for N-bromosuccinimide. And the structure looks like this, a little bit sassy in there. And what happens is now this bond, my pen, well, this bond right here is going to break and give us a bromine radical. Now, we're not going to draw the mechanism to this one. N-bromosuccinimide reacts in a couple different ways. It will give a bromine radical. It also is a really good source of just Br2 without having to use elemental bromine. There's probably 5 different mechanisms you could look up for NBS, and they're all going to look a little bit different. The one thing is that NBS can be quite selective depending on how you're reacting it. So in this particular reaction, what NBS does, and whether that is the actual succinimide radical, they tend to be actually a little bit stable, which is what makes this such a powerful reagent. Or it's one of the bromine radicals. I'm not sure anybody could even tell you that. But one of these radicals abstracts a hydrogen right here. Not a two-headed arrow. So we're going to do that hydrogen abstraction. And why that one? Okay, this is so specific. And why it's different even than the top reaction that we looked at. When you leave behind this radical, it is called allylic. Allylic is next to a double bond. It is very specific. So in other words, something like this is not allylic, only this is. It has to be next to a double bond. And those allylic radicals, I feel another list coming on. Okay, our radicals, tertiary was awesome, secondary was okay, primary really sucked. Allylic ranks higher than tertiary. So that allylic radical is even more stable and even easier to form than a tertiary. So this intermediate is definitely key in that NBS pathway. And then a termination then could be that we react that bromine right there, and that's how we make that product. So I won't, if I don't give you a full mechanism, I would never ask you a mechanism. So I do like to give as much information as I can, and sometimes mechanisms just simply aren't known. So NBS, though, however, is very specific. You will add that bromine allylic to your double bond. It's awesome. They're very specific. So, and it's a much easier reagent. It's much more modern. I can't remember exactly what year NBS came out, but I'm going to guess late 70s to 80s. It might even have been closer to the 90s. We have it in our lab. It is a much easier way of adding bromine to substrates. So it's pretty awesome. All right, let's take a screenshot of that, and then let's move on to our last round of bromine reactions. So let's move on to those. And then we've got to probably list them and apply them in another video. There's so many of them, aren't there? So let's start with the basics on this one. And then we're going to give ourselves some space to really draw out these reactions with some stereochemistry. So let's start with the basics. First thing that we notice is that our bromine source is now back to Br2, not HBr. So we have just changed our bromine source. We now have Br2 in there, elemental bromine. Now, do you notice this is not light, this is in a solvent. So this is not radical. This is going to be a completely different kind of pathway. This is not radical. If we were still meeting for OChem 1 lab, this would be one of the experiments that you do. So I think you're still meeting for lab, you just don't get to actually touch the bromine in lab. You're gonna watch a video. Oh, so not fun, right? All right, so let's start to look at our mechanism. Let's draw out how in the world this thing can happen. Let's take our alkene and our elemental bromine. All right, this is one of those things that you explain on paper and you don't believe it and it seems silly, but when you actually do this chemistry and it happens in a couple seconds, then you believe it. So our bromine is extremely nonpolar. And likes dissolve likes, and sometimes our nonpolar reagents react just as fast, if not faster, with very nonpolar reagents. And our alkenes are actually quite nonpolar. So in your heart, you would think you'd kind of mix them and nothing would happen. But you can literally add a drop of bromine to a double bond, and within a second or two, that bromine, which is red, will go colorless. It is just added to that double bond that fast. It's pretty cool to actually see it. So how do they even react with each other? Well, first of all, as they get close in space, we're going to go back to Gen Chem 1 for a second with those intermolecular forces. All you have here is an induced dipole. It's really funky. You just have dispersion forces. So as they get close to each other, for a split second, this big ball of electrons around bromine is going to end up around the other bromine. So if you want to look at electron density, just for a split second, as these two get close to each other, the electrons are going to repel each other. And what that does is induce a dipole. So on that first bromine then, you kind of scared away your electrons, so you've got a partial positive, and they kind of ran over to the other bromine. Now you've got an electrophile. So we've got a space now here for those electrons in that alkene, and they can displace, do a nice SN2-like reaction on bromine. So then what do we make from there? Remember, we get to swing both ways. So let's draw both of those. We can end up forming our bond up here or out here to bromine. Okay, now here's the awesome part. We just added a bromine and not a hydrogen first. So what's the big difference between bromine and hydrogen? Electrons. Bromine is huge and there is a crap ton of electrons around the outside. So for either one of these, even though we would likely pick this one as our winner, it doesn't actually matter because bromine has a ton of electrons around it. It is going to fill in that space. And then look what happens. Both of them end up making the exact same thing. And it's called a bromonium ion. So you've got a bromine here, only there's a plus charge there. You just made a ring with that bromine. You can't have a big empty hole next to that bromine and not have it fill in. It's just not going to happen. So are we done here? No, this ring is actually quite reactive because you've got to give a lone pair back to bromine, and it's in a 3-membered ring. That is going to have a lot of ring strain and just wants to spring open. So the only thing floating around in your solution is your solvent and that Br minus you lost. So Br minus is going to do an SN2 reaction on that bromonium ion. And that is how you make that product. We end up literally substituting 2 bromines where that double bond was. Old school chemists call this an alkene test. If you had a mysterious solution and you wanted to know if it had a double bond, you'd add a drop of bromine and see if the color disappeared. If our bromine went from red to colorless, you know you have a double bond. Those reactions happen that fast. Okay, now in the real world, you don't actually want to add that many bromines. Anytime you add a halogen to a carbon like this, you're making a nice carcinogen. You're also making something called a lacrimator. A lacrimator is what squeezes your eyeballs and makes you tear up. So like when you're cutting your onions, that's a lacrimator. In fact, the original tear gases, that's where the name comes from. That is the tear and tear gases. They are halogens, and they are hitting your eyeballs. They are lacrimators. Okay. Oh, I feel like drawing a little eyeball in there with a little tear on it. Those are lacrimators. All right, so let's do this in a ring, but let's get a little bit sassier. Let's do a little bit of stereochemistry here. Now, in a substrate like this one that we just did, there's no stereocenters there. But this is why we then put it in a ring. So now we've got to consider stereo and stereocenters. So go ahead and screenshot for a second. Let's draw this prettier, and let's draw it down here for that ring. And let's include some stereochemistry. And this reaction's been around for long enough that it has absolutely been studied for stereochemistry, so we know that. All right, let's start then with that very first step. And I'm going to try and draw just a little bit smaller so we can fit it all on here. We've got that bromine induced dipole. Our electrons here from our cyclohexene. We're going to go right out like that. Now again, we've got some choices here. We can add our bromine, can go out here. We leave behind a carbocation. Or our bromine can add here, and we leave that carbocation. And again, we left behind a bromine minus. Okay. All right, so we've got some choices there, but now we also have some stereo to consider. Okay, we do have flat, our carbocations, remember these are flat, but didn't we just make a stereocenter? We did. Now this is flat, but this isn't. So our bromines, these reactions, especially with those carbocations, they are actually going to be racemic. They will be 50-50 on either side. And now remember, your bromine is going to fill in that carbocation anyway. So what we're about to get to in theory is that same ring structure, but let's go ahead and then add stereochemistry to that. So we just made that bromonium ion. Except now in those rings, if you've got a model set, you take a second to build this. This is awesome because you now have a racemic mixture. In those rings, you will have an up and a down in those rings. So we just got bigger. We are about to redraw this. What does that really look like? They are not flat and they are not stuck to each other, you know, fused. They're fused, but they are 3D. So that bromine ring can be down with our little bromonium ion. Okay, or that bromine ring can be up. That could be on the top face or the bottom face of that ring. If you were to model that, you would see that those rings aren't just flat. One's up and one's down. Okay, now why do we care? Because, just wait for it. This is so much fun. Just wait for it. What's the only thing left that's going to add in there? It's our bromine minus. I feel a color code moment coming on. Let's color code that green. And this is going to get big. All right, guess why? That bromine minus, when it adds in, this is a nucleophile, and when we add in and open that ring, it is an SN2. Okay, why do we give a crap if that's an SN2? Oh my gosh, what does SN2 do to stereocenters? Inversion. Oh, this is going to get fun. And not only do we have SN2 inversion, but guess where that Br minus can add? Here, 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 and here. Holy crap, get out a fresh piece of paper and some colored pencils. Let's do this. All right, let me take all 4 of those and let's draw the options. Let's kind of draw them right down here. Let's take this one. All right, we've got here. Give me a second to draw these. All right, all of these are bromonium ions. Why did I draw 4? we have a top face and a bottom face, and we have 4 different places for that bromine to add in. So, all right, let's start with that top one. Our Br minus can do an SN2 right here. And then what happens? This ring springs open. Oh, let's draw it. This is so much fun. It's like we took alkenes and stereochemistry and SN2 and put them all together. Okay, sweet Jesus, what do we do to that stereocenter? Well, that Br minus is coming in on the top. It is inverting that stereocenter. It is literally forming a bond on the top, and it is pushing that methyl down. So your Br minus is like that. Well, then what happens to the other bromine that's already on your compound? Well, that is just released, and it stays right there. Okay, you just sprung open that ring. These electrons go with that bromine. And now look at that. We've got 2 stereocenters. This is fun. All right, let's do it again. All right, what's our another option? What about this bottom one? Oh, that's too big. That's ruining my Zen space. Okay, so let's try another one. Where's the other option? Well, our Br minus could also go here and invert that stereocenter. So let's draw that. All right, so then that means the top stereocenter stays the same. That did not do an SN2. We just opened that ring. So these electrons opened with that bromine. And now from which direction did this bromine add? Well, it's coming in from the top, and that is inverting that stereocenter. That stereocenter was dashed or on the bottom, and now it is on the top. Awesome. We just created 2 stereocenters there. Are those compounds the same? I think we ought to play my favorite game at the end of this video. Which one's the same, and are they the same or are they different? It's one of my favorites. All right, let's keep going. We have 2 more. All right, what's our option then for this second one? Are these really different? Heck yeah. All right, now our bromonium ion. Ooh, we need the charges on all these. I just really wish we had a huge board right now, don't you? All right, so now our bromine minus, couldn't it also go right there? SN2? Absolutely. Let's draw that one. All right, so now where are you coming in from, the top or the bottom? Well, you have to do an inversion. So you're coming in from the bottom. So now you're making that bond to bromine. And then the ring is just springing open. You did not invert this stereocenter. And you just opened that ring. Okay. All right, we've got one more. Let's do it. So now this one, bromine. Our bromine minus can come in down here. Open that side. So that means that that top part of our ring can stay like that. We did not invert that stereocenter, but we did invert the bottom stereocenter that is coming in from the bottom. And there is that bromine. And then these electrons ended up right there. Holy crap. All right. So remember our stereocenters. We just made 2 stereocenters. Remember then, we have 4 possible stereoisomers. Did we make all 4, or are any of these the same? So pause for a second. I'm going to sip my Starbucks. If you can't tell by this video already, I actually had a Starbucks today. Okay, so let's take a look at them. Are any of them the same? Yeah, aren't these the same? And then aren't these the same? Yeah. So we actually had 4 possible, but we only made 2. So these are stereo selective. All right, I got to say that again. That's a vocab. We had 4 possible stereoisomers that could come from that reaction. We only made 2 because these are the same and these are the same. And in fact, did we make cis or trans? We made trans only. And that's because of that SN2. You'll notice we made only trans out of this reaction. Because that second part is an SN2, we invert that stereocenter. So these reactions are stereoselective. They are not stereospecific. I won't ask that vocab, but if we were to get only 1, it would be stereospecific. We are stereoselective. We got 2 out of 4 possible. We got the trans for that. So let's just add some stereochem up here. So what did we really get here? We have to get these trans. So we have bolds and dashes in there to make sure that those bromines are trans. Okay, awesome. That's so fun. I love it. So you may want to practice some of these. And then I'm going to pause this video and we're about to turn around and do bromine again, but wait for it. We're going to change the